Scrum is an agile management framework designed for efficiency and collaboration. It revolves around sprints, which are 1 to 2 week work cycles, each with clear tasks and goals. A Scrum team has the Scrum Master who ensures smooth communication within the team, the product owner who liaises with the client to align with project requirements, and the development team who implement code changes to meet the sprint's objectives. Before each sprint, a sprint planning meeting is held to outline goals and assign tasks. At the end, we conduct a sprint review to check what was accomplished, followed by a retrospective to reflect on the sprint effectiveness and learn for the future. We rotated the Scrum Master role each sprint, giving every team member the opportunity to build leadership and facilitation skills, while also bringing fresh perspectives and varied approaches to problem solving and team management. The order of Scrum Masters went Boxu, me, Will, Max, and then Savannah. We all delegated tasks and made sure we hit the product requirements from the clients. This rotation fostered a collaborative environment where every team member contributed unique leadership and technical insights. Our Scrum meetings were highly effective. We placed strong emphasis on collaborative delegation during planning meetings, which ensured that every team member was engaged and motivated with their assigned tasks. This approach allowed for a sense of ownership and kept everyone invested in their work. Additionally, our sprint evaluation meetings proved effective as well, providing each team member in the opportunity to share updates on progress and maintain alignment. Our Scrum meetings were effective but could be improved in 2 key areas: time management and focus. To keep meetings efficient and on schedule, we should have ensured discussions remain concise. Additionally, we should have shifted the emphasis from updates to more planning and strategic discussions. This would have helped set clearer goals, align the team, and better prepared us for upcoming tasks and challenges, making our sprints more effective. Reflecting on our Scrum process, we excelled in key areas. Effective task delegation enabled seamless collaboration and meaningful contributions that aligned with our project goals. Our well-organizing planning meetings clearly defined tasks and ensured timely execution, maintaining an efficient workflow. Sprint retrospectives provided valuable opportunities to assess our processes, learn from experiences, and make improvements for future sprints. I would consider changing for future projects, incorporating daily stand-ups rather than weekly meetings. This would enhance team communication, allow for quicker problem resolution, and maintain a consistent flow of updates. However, due to the university workload, including 3 other courses, and team members balancing jobs, daily stand-ups were not feasible for this project. Our team communication was highly effective throughout the project. Using Discord as our main platform, we stayed connected and shared updates seamlessly, including holding weekly meetings in a familiar setting. Organizing channels by topic made information easier to find, keeping conversations clear and focused. This structure improved collaboration, ensured quick access to relevant details, helping us stay aligned and move forward confidently.
I will overview the requirements for our project through discussing the requirements gathering process, outlining how we approach understanding the project's needs. Then I will attempt to outline how we gathered requirements effectively, and then highlight major requirement changes that occurred during the project, focusing on their impact on our work and how we adapted to handle them effectively. We began with a thorough review of the project brief provided by Insight Factory and validated our understanding through initial team discussions. This process helped us understand the need to develop the predictive maintenance model to detect rail breaks using the dataset provided by ARTC. By identifying critical technical needs early, we could effectively guide our project scope. Through continuous requirement reviews, we stayed aligned with the project's goals and adapted our approach based on performance feedback. First, we held weekly requirement review meetings every Tuesday on Discord. These structured meetings allowed us to go over any updates or changes to the project's requirements in real time. This was crucial in keeping everyone aligned and aware of the latest project's goals and tasks. To ensure a clear record of our discussions, we documented all meeting notes and updates in Google Docs. This way, any decisions, action items, or adjustments were accessible to the entire team and could be referred back to as needed. This was hosted through the God document. As project requirements evolved, we found ourselves needing to adapt quickly. This often involved conducting additional background research. For example, when explainable AI was introduced as a requirement, we had to research different XAI techniques at length to understand how to incorporate them into our project. Using Discord allowed us to have real-time communication on these matters. We could quickly clarify any ambiguities or changes to the requirements, which reduced delays and helped keep the project on track. Finally, to stay organized, we structured our Discord channels by sprint. Each sprint had its own dedicated channel, which made it easier to track progress and focus discussions relevant to each phase of the project. Overall, using Discord for structured real-time communication combined with ongoing documentation enabled us to adapt effectively to changing requirements while stay organized and on task. The following covers 3 major changes we encountered in the project's requirements and how we adapted to each one. Firstly, when explainable AI was introduced, we had to conduct further research and implemented methods to improve model transparency. This was far different to other requirements as it involved greater documentation and greater research. To optimize performance, we refined our hyperparameter tuning and data balancing techniques. These helped out our F1 score and were also utilized for recurring requirements. Further, improving dataset quality through feature engineering also became our priority with different requirement changes. We had to adjust our production line to support concurrent model experimentation, enhancing our workflow greatly.
At the start of our project, our group's vision was to train a machine learning model that could generalize the unseen data, accurately identifying real segments at risk of breaking. This vision established the foundation of our definition of done, ensuring every deliverable aligned with our ultimate goal, which is to train a model with processed data that would generalize/predict from unseen data in order to identify all possible real break locations with high accuracy and advanced score. While each sprint had its own specific definition of done, each of these were purposely created to address each individual user stories for each stage of development. All consistently contributed to our overarching goal. For example, in Sprint 1, we concentrated on researching data preprocessing, feature engineering, and machine learning techniques. Therefore, the definition of done for Sprint 1 centered on completing and documenting this foundational research, giving us a clear understanding of the best approaches for our model. In Sprint 2, our focus shifted from theory to coding. We began implementing the insights gathered from our research into code. Here, the definition of done evolved to contain more about code implementation and initial model creation, reflecting our progress towards a working predictive model. As the project progressed, each sprint's definition of done adapted to the evolving requirements of that stage, whether it was hyperparameter tuning and accuracy improvement in later sprints, or achieving model explainability to build stakeholder trust. Despite these, all the definition of done aligned with our primary objective. Each sprint contributed incrementally to our vision for a useful, accurate rail break prediction model, and therefore our definition of done, while adapted per sprint, stayed in line with our goal. Therefore, I wouldn't consider our definition of done have evolved, as in the end, with everything contributed to a model that reflected the consistent vision we set at the beginning of the project.
Next, we're going to talk about the tools that we use for our project. In this project, we used a variety of languages, frameworks, and libraries to build a working railway predictive model. Python was our primary language of choice for its benefits in the world of machine learning, such as vast selection of libraries and integrating smoothly with Spark through PySpark. SQL was vital for querying and organizing datasets in Databricks, helping us efficiently retrieve and store our data. Spark was essential for processing the massive rail datasets at scale. However, when Spark was incompatible, we used pandas. NumPy was used to handle the numerical computations across workflows. And ImbalanceLearn helped us address the class imbalances through Smote. Scikit-learn was used in the pre-processing of our data for its functions such as an imputer and scaler. XGBoost is an example of one of the model libraries which was chosen for its efficiency and accuracy with structured data. SHAP is also an example of one of our explainable AI libraries used to help understand what features were contributing to the output scene. Optuna was used to help us tune the hyperparameters of our models. Matplotlib and Seaborn were utilized for their exploratory analysis, helping us visualize what was happening with the data. For communication, we use Discords and Teams for team coordination and client interactions, while Google Docs and Google Drive organized our project notes and reports. GitHub helped us track the project tasks across sprints, and the Insight Factory platform helped manage our workflow and pipeline. Integrating Databricks as well for our primary coding environment and data manipulation for model testing. Two tools we couldn't fully use on the Insight Factory platform were PyTest and Spark's vector assembler due to some technical constraints. While PyTest would have supported code robustness, we compensated by inspecting function outputs closely, and the vector assembler could have helped us streamline data vectorization. Instead, we had to convert to pandas where needed.
Our approach to testing the software focused on ensuring the models and data processing steps were functioning as expected by performing tests directly on the data and the model outputs. Specifically, we use three main methods. First, running implementation on datasets and visually inspecting the resulting data tables to verify correct data transformations. Second, we tested our trained models on validation sets drawn from the training data and evaluated metrics like F1 score, confusion matrix, precision, and recall to assess model performance. Finally, we ran inference on trained models to generate predictions, which we submitted to a leaderboard that provide additional feedback on F1 score. This approach allows us to catch high-level issues and validate the model's overall functionality. However, we did not implement unit testing or test-driven development. Using test-driven development could have benefited our project by ensuring each function or component was fully validated in isolation, catching errors earlier in the process, and improving code reliability. Although it wasn't feasible with our current workflow, given the focus on data-driven model evaluation, test-driven development could potentially enhance future projects by establishing a stronger foundation of unit test. While our process was effective on a broad scale, it lacks the fine-grained testing needed to catch smaller bugs early. Without unit tests, some issues went unnoticed until they impact other functions, which slow down our progress. Many of these bugs could have been identified sooner with a structured testing framework. In hindsight, incorporating unit tests for key functions would have added an essential layer of verification, reducing errors and make our development process more robust overall.
Throughout the project, our group demonstrated strong progress and active participation in the initial sprints, but faced challenges that ultimately impacted our performance later on. We began Sprint 1 with a clear understanding of the project objectives and an eagerness to explore data engineering and machine learning solutions for predicting the real breaks. Comprehensive research findings were compiled into concise documentation. Our drive to succeed was carried over to Sprint 2. When we began familiarizing ourselves with the software platforms like the Insight Factory Workspace and the Azure Databricks, we remained committed to upskilling ourselves as most people were relatively new to working with large imbalanced datasets. While this process was time-intensive, it equipped us with the foundational skills and laid the groundwork for future stages. At the end of Sprint 2, we successfully submitted an initial model to the leaderboard. Our group momentum was sustained to Sprint 3, where the first model accuracy requirement was released. We needed to achieve an F1 score of over 55% on the test dataset. This sprint saw our first inability to fulfill the acceptance criteria. We only managed to achieve a score of 47% because of premature data processing techniques. In Sprint 4, we were given 2 user stories. The explainability AI research in Story 4.1 was fulfilled and compiled into a shared report by a third of the team. However, due to project management challenges, our progress on the machine learning model was impeded. Both our Scrum Master and key team members were overseas. Logistical challenges limited their availability and slowed our communication and task execution. By Sprint 5, our team engagement had noticeably declined. In the absence of a strong driving force, some members became less proactive, resulting in incomplete tasks carrying over between sprints. As a result, our final model achieved an accuracy of 49.48%. If we could restart this project, we would first prioritize a more robust project management structure, such as assigning an additional co-scrum master or a backup leader to fill in when primary members are unavailable. We would also adjust our model architecture to enable parallel execution of different feature engineering and selection modules. This would reduce dependencies, enable isolated testing, and encourage data experimentation. Finally, we will recommend holding time-boxed meetings. It would have helped us stay focused on critical tasks during each meeting, potentially improving productivity despite the lower engagement levels.
Overall, documentation was a strong point for our group. We created a variety of documentation processes for each component of our project. Having separate processes for each component enabled our group to use different methods which were suited to the context of that component. This separation also made it easier for group members to quickly and easily find the information they wanted. Since the project involved a wide range of distributed resources, we created a Google document which we called the God Doc. This organized all resources by providing links to them which we grouped together in an intuitive way. The sections included main items located at the top for quick access to critical sections. This was followed by a group assignment section for the reports and presentations throughout the project, and the remaining sections consisted of resources for each of the 5 sprints. The God Doc proved to be incredibly useful for our group as it effectively organized our information, enabling the group members to access the resources they needed quickly and easily. As we adopted an agile development approach, we used GitHub Project Board to track and update our ongoing work.
This offered distinct sections for displaying how a task was progressing and assisted our process by enabling us to create individual tasks for each sprint that were assigned to group members. This simple and collaborative approach was effective in giving all group members and the client a clear overview of how the project was advancing. For the production line, we employed multiple documentation processes for outlining what different components did and how to use them. This included embedding descriptions in the metadata tab of the production line tasks to outline details about its hyperparameters. We also added lots of comments and markdown cells within our notebooks, and finally we created a Google document to provide an overview of what each task did. This approach provided plenty of information to group members and any future users, such that they could quickly and easily understand what something was and how to use it. In retrospect, defining a more formal approach to how comments and markdown cells were added would have been beneficial for our group, as our approach to this was informal and consequently inconsistent. In an effort to create an effective model, our group performed lots of experimentation with multiple data processing techniques in combination with various machine learning models. We created a Google Sheet where each row consisted of a model submission and the columns outlined the model's performance and components. This was assisted by app scripts, a built-in feature providing the ability to sort all rows based on the F1 score, which organised the results so group members could quickly and easily see what was effective and what wasn't. This was beneficial as it enabled our group to reduce repeated experimentation and benefit from each other's findings, helping to guide our direction of experimentation.
Hi everyone, my name is Feng Yuan and I will be introducing the software analysis. During the development of our project, we observed certain practice that is likely contribute to higher quality code and smoother team collaboration. The first one will be pull request management. One key factor was our approach to pull requests was we aimed to keep them focused. Our implementation was split tasks into each individual person, so it is easier to follow, but it provides less explicitity. Like for improvements, we could split further to create even more smaller pull requests. This not only providing a more clear requirements, but also would help preventing large and complex merge and encourage more frequent code reviews. For example, one instance of this was when we had a model update by breaking down into smaller pull requests, like each focused on a single aspect of the model. Like for example, like data, like parameters, like feature engineering, like methods, and we managed to keep our code base stable and reduce conflicts. Another element that contributed to better code quality was ensuring that reviewers were those who had previously worked on this section of code is defined. This increases the effectiveness as reviewers already understood the context and the potential impact of change. This familiarity means less time spending onboarding during each review and more focused feedback, which speed up the iteration process and lead to more refined code. And for the data analysis, reflecting our progress, there are some analytical questions that provide valuable insights. Like for example, how did the frequency and size of pull requests impact our bug rate and overall team velocity? Like this question could reveal like a direct correlation between the request habits and the quality. Like for the data requirements, like to analyze this, like data on like size and code review durations, the number of bugs identified during like the post-merge, and time taken to resolve those bugs. And for the hypothesis, our hypothesis is that it's smaller and more frequent correlate fewer bugs and faster team velocity, like supporting the theory that the process is more sustainable than larger effort. And another one is like, what feature have highest impact on model predictions? Well, it will be the like the feature importance scores, like model weights, like calculated their sharp or lime technologies, and their hypothesis is like certain features like specific center data contributes significantly to the model's predictive power. Like identifying this can help optimize data collection and model focus.
Reflecting on our group process, the three main strengths stand out: effective meeting management, consistent communication, and a collaborative approach to problem solving. First, our meeting management was well organized. We held regular meetings with structured agendas, ensuring each section covered essential updates, any blockers, and clear next steps. In our weekly meetings, we discussed each member's progress and any challenges encountered. This kept everyone aligned and allowed us to tackle issues before they affect our timeline. This organized approach helped us stay on schedule and kept every member aware of the project's current status. Second, we maintain a strong, consistent communication through Discord, allowing us to share updates and discuss solutions quickly. For example, when we encounter issues in data preprocessing, like handling missing values in critical fields, Team members actively share potential solutions on Discord, such as imputation methods and relevant documentation. This proactive communication meant we could resolve issues efficiently without waiting for the next meeting, minimizing downtime and keeping the project moving forward. Finally, our collaborative approach to problem solving was a strong point. When facing complex tasks like optimizing model performance, we often work together to brainstorm solutions. For example, when one member proposed a feature engineering technique, others would build on it, adding ideas that strengthen the final implementation. This collective approach not only improved the quality of our work, but also fostered a sense of teamwork and ownership, motivating everyone to contribute their best. Overall, these streams allowed us to work efficiently and achieve a cohesive result, strengthening both our process and our final product.
While our group developed an effective set of processes which enabled us to advance towards our goal of creating an accurate predictive model, our final process had some noteworthy weaknesses which impacted our group's performance. Our production line was created with the intention of identifying the optimal set of data processing techniques so that we could have finalized versions of the train and test datasets. However, we actually found that different data processing techniques worked better with some models and worse with others. This negatively affected us, as group members had to continually rerun the tasks to create datasets with their preferred set of modifications, costing our group time and reducing the ability to work simultaneously. In future, we would alter the production line so each person has their own copy of the datasets, avoiding the need for anyone to rerun the tasks each time someone else modifies their own datasets. While our machine learning results documentation contained 40 entries, our group actually submitted many more attempts to the leaderboard over the semester. Not adding all results to the documentation hinders our group's collective understanding, which leads to repeated experimentation or exploration in known ineffective directions, thus hindering our progress. Furthermore, only 4 out of the 8 group members actually added to this documentation. This obviously negatively affects our group's progress as less people are contributing to the advancement of the project. This was mostly a product of the steep learning curve of the Insight Factory platform, in combination with the shared, slow cloud cluster. These factors discourage group members from contributing. So in future, spending more time learning how to use the platform and getting access to a faster cloud cluster would benefit our result. The requirement for training explainability and inference explainability led us to invest some time in researching explainability AI techniques. While we did end up using techniques such as SHAP to calculate feature importance from the training dataset, our group's focus on trying to increase the F1 score distracted us from integrating any inference explainability. This negatively impacted our group because it means we did not meet the client requirements and therefore delivered an unsatisfactory product. Next time, our group will improve on this by having a set of core requirements from the client, which we revisit at the start of each sprint to ensure our planning takes them into account.